Okay, let's get started. So first off, how did you, for those who took the quiz, don't give it away, but do you find it easy, hard? So I tend to make it like, the point is not to trick you, it's just to make sure you're not too far behind. So as you can see, a lot of it's just testing whether you know the definitions or not. So, okay, let's share screen. Okay, so let's get started. So today we're gonna go over something new. It's called a group. So before that, the professor set office hours to be, I think, Monday at 5, Friday at 4. So what times do you all prefer I have my office hours? So I'm guessing maybe sometime like would Monday, Friday. I mean, he has it 2 and what is it? 2, 4 and 5, or maybe I could do Wednesday. I mean, I don't want to do a time similar to his, so maybe let's do 2 to 3. Does that work for some of you? Anyone? Is that good? And then I'll just put more by appointment. Yeah. Okay. So let's move on. So today we're gonna go over what a group is. So the idea is we want to characterize sets we know, like integers, natural numbers, rational numbers. And the point is, a lot of the time they form a group. So okay. So let me just define a binary operation, right? Is on a set G. It's just like, think of it like your usual operation is like addition, multiplication, right? Is a function from G cross G to G, right? Sometimes they do this, right? It takes AB to A circle B, or they might write AB, yeah. But a binary operation circle, yeah, it's A circle B. But sometimes they write like just AB. If it's like understood, it's that operation. So a group G with this binary operation. So again, some later on we might not write what the binary operation is. If it's understood, we might just write like a group and then capital G. It is a set G with binary operation circle that satisfies three properties, right? So the first one is associativity. So I'll call it associativity. So if you do the binary operation, it's the same as doing it with A to B first and then C. And then your group G has to have an identity element. So there exists identity element E in G such that, it's exactly what it sounds like, right? So when you do the binary operation with any other element in G, for every element in G, you get the same thing back. And then for all A and G, so this is the important part. There exists A inverse in G, and this part is important. So in G, yeah, such that, you know, A circle A inverse is A inverse circle A is the identity. Yeah. So a group G has associativity and an identity, and then every element has an inverse. Yeah. So is everyone comfortable with the definition so far? So I think the best thing to do with something new like this is think of examples and non-examples. So example would be integers under addition. Yeah, so here, this is my circle, and this is G. Yeah. So certainly let's reinterpret it, right? So 1 is just saying A plus B plus C is A plus B plus C, right? So that's certainly true, right? Hopefully you all know this by now. And then what is our identity element? So what integer such that when given any integer such that when I add it, I get the same thing back? So what number does that? Yeah, 0, right? So E is 0, right? E is 0, right? Because for all integers, right? Because for all A and Z, A plus 0 is A, and 0 plus A is A, right? Okay, so does every element have an inverse, right? So if I give you an integer, what's the inverse? So given A and Z, what's the inverse of A? I need it. What's the number that I add so I get 0, right? I want, A plus something equals 0. What is that something? We all know this, right? It's negative A, right? So A inverse is negative A, right? Let me put A inverse. And the important thing is negative A is in Z, right? If A is in Z, negative A is in Z, right? Because integers includes all negative numbers and all positive values. So this is a group. The integers under addition is a group. Okay, everyone good so far? Good. Okay, so now let's change it up a bit, right? Integers under multiplication. So here, what's the associativity? This is still certainly true, right? I mean, sorry. I don't know why I put print. So A times B times C is the same as A times B times C, right? This part is certainly true. Yeah, because they're all equal to ABC, right? So, oh, by the way, this is, for all A, B, C, and G. I forgot to write that. Okay. So now what would the identity element be, right? I need something where A times the identity is A. So what number should that be? Yeah, it has to be 1, right? It can't be anything else. So E is 1. And that's certainly true, right? A times 1 is A. 1 times A is A, right? Okay. Now 3, here comes the tricky part. What would be my, do I have an inverse? So if I given, like, let me just say, pick a number, like 2. What number do I need to multiply to get the identity element 1? Yeah, 1 over A, right? So 2 times 1/2 is 1. This is 2 inverse, right? Now here is why I put the blue thing here, right? The inverse has to lie in G. Is 1/2 in the integers? Yeah, no, right? So you see that, 2 has no inverse. So Z with under multiplication is not a group. Yeah, it doesn't satisfy the third property. Okay, everyone good so far? Hopefully more examples is good. So now let me just take Q under multiplication. So hopefully you all know what Q is, right? It's the rational numbers. So certainly this is still true, right? A times B times C is A times B times C. And the identity element is still 1, right? A times 1 is A, 1 times A is A, right? For all A, B, C, and Q, and for all A and Q. So we're back at the, here, right? Does every element have an inverse? Yes or no? So does every element in Q have an inverse? Yeah, 0 doesn't, right? So remember 0 is in Q, right? But 0 has no inverse. Right? Because I mean, if 0 had an inverse, it would mean 0 times 0 inverse is 1. But no matter what element you choose here, 0 times whatever number is 0, right? It's not 1. So you see that Q under multiplication is not a group. Yeah. I mean, 0 was an issue for integers too, right? In fact, other than 1 and -1, every other integer has an issue, right? Because like 2, 1/2 is not in it. 0, same problem. 3, and any number other than 1 and -1. But for Q, the only problem is 0, right? So let me just say exercise. You can check this thing without 0 under multiplication is a group. Yeah. So hopefully that convinces you, right? I mean, we sort of did most of it already. So is everyone clear so far? Okay. Now let's move on to more stuff. So there's something called Z mod NZ. So these are, remainders. I think I went over this first lecture. Mod n. So it's the remainders you get from when dividing by n, right? So you have like many classes, right? You have remainder 0, remainder 1, remainder 2, all the way to remainder n minus 1, right? And let's do that under addition. This is certainly a group, right? Because let me just say, you have to check this, but let me just say check, A plus B plus C is equal to A plus B plus C. I mean, the idea is if I give you a number, like just think of like the number 12, right? If I give you a number that has remainder 1 when dividing by 12, and then a number with remainder 3 when dividing by 12, if you add them up, you'll get a number with remainder 4 when dividing by 12, right? it's pretty clear. It's pretty clear that A plus, you could, you just use this. This is certainly true, right? I mean, an example would be like, if I'm doing mod 12, right? Like 13 and what? 17, yeah. So 17 has remainder 5 when dividing by 12. 13 has remainder 1. I mean, when you add this, you get 30, and you should get remainder 6, right? Because 12 goes into 30, like 12 times 2 is 24, right? So you could check this. And what's the inverse? Well, the inverse is just 0, right? If you believe this holds, then A plus 0 is A plus 0, which is A. And the inverse is clearly, so you think about this, it's negative A, but the class of negative A minus A is 0, right? But if you want to write it in terms of this, how do I write negative A in terms of, if you want to just, this works, but, how do you write it in terms of these representatives? Right, so what's negative 2? Like mod, let's do mod 6. So I have 0, 1, 2, 3, 4, and 5, right? So the inverse of 1 is negative 1, right? But what is the class of negative 1, right? How do you get that? I mean, what is the, in terms of these, right? So just like how the class of 7 is 1, right? Because 7 and 1 have same remainder. Well, how do you go from 7 to 1? You subtracted 6, right? And same for 13, right? You subtract multiples of 6. Well, similarly, negative 1, you can add multiples of 6, right? So if you add 6, you get 5. So you see the class of negative 1 is the same as the class of 5. And so on and so forth. So Z mod NZ under addition form a group. I mean, it better be, right? It was one of our examples from the start. So yeah, n minus a, or yeah. So again, negative 1 plus 6 is 6 minus 1, right? So you could do n minus a or negative a plus n. Okay, so moving on, let me ask you, Z mod NZ under multiplication. So obviously from previous examples, right, 0 is a problem. Let me write class of 0, right? Because there's no inverses, right? So by the way, you could also check A times. This is still true. Yeah. So 0 is a problem, right? Because our identity has to be 1, right? The class of 1. And the same thing happens. But let me ask you, other than 0, are elements invertible? Which elements are invertible? I mean, which elements have an inverse, right? So let's go over, this certainly is not a group under a multiplication, right? Because 0 is a problem, but you see other elements are a problem, right? 2, 4, 6. These are not invertible, right? I mean, to check this, you just multiply by every representative, and you could check this. So why is it not invertible? Does anyone have an idea? So it's because if they share a factor with 8, share a factor other than 1 with, yeah, so they're not co-prime. So GCD of 2 and 8 is not 1. So why is that the case? Well, let's see, right? If GCD of A, I'll just call it A and 8 is 1, what do you all know by definition? Right? I think remember, so there exists x, y, and z such that ax plus 8y is 1, right? That's one of the nice things about GCD, right? I think from the first discussion, you could write it as a linear combination. So question, what happens when I mod 8? The whole equation. So I divide out by, I just take remainders when dividing by 8. This thing, I mean, it's the class of AX, right? And what is this thing? This thing is the class of what? It's the class of 0, right? Because it's divisible by 8. So this is just 0. And this is the class of 1. And then voila, you're done. Because this is A times X equals 1. So X is your A inverse. Let me write it like this. Right? Because it's the number that when you multiply by A, you get the identity, right? So it's the inverse. So and then you can work backwards. So if you're invertible, then GCD is 1. But you see that if GCD is not 1, your element is not invertible, right? So that should somewhat convince you. Okay. Everyone good so far? Hopefully, I want to do a lot of examples because this is some new stuff. So, okay, let's continue. So note, let me just say note, there is no requirement A circle B is B circle A, right? If you go to the definition, right, no one required that. Even though in all the examples I gave you so far, it's true, right? 1 plus 2 is 2 plus 1. But note that there's no requirement for this, right? So if A circle B is B circle A for all A, B, and G, then we say G is abelian. If not, we say G is non-abelian. Okay, so let me go over an example. So let's let M2R be set of 2 by 2 matrices over R. Yeah? By over R, hope you all know what that means. That means like all the entries belong to the real numbers. So obviously you could check this as a group, right? So, sorry, plus. I don't know what I was thinking. Plus, yeah. So really quickly, you can check, make A plus B. This is linear algebra, right? If you add matrices, this is certainly true. I guess math 3A. And what is the identity here? What matrix, such that when I add any matrix to it, I get the same matrix back? So what is my identity here? And should not be that hard. I need A plus something is A. So when you add matrices, right, it's component wise, right? I mean, I need a matrix. If I call this A, B, C, D, I need to add something such that I get A, B, C, D. It's pretty clear it's the 0 matrix, right? So I'll just write this as 0 is the identity, right? Now 3, the inverse is clear, right? If A is A, B, C, D, then A inverse is negative A, negative B, negative C, negative D, right? If you like, people normally write negative A. Everyone clear so far? Good. Okay, let's make this harder. So M2R. This, of course, the 0 matrix has no inverse, right? Same problem. But question, what matrices do have inverses? You should all know this. It's Math 3A. So in general, other matrices don't have there are other 2 by 2s of no inverse. So how can you tell if a matrix is invertible? So Math 3A. If I give you a matrix, yeah, determinant being 0, right? So if determinant of A, B, C, D not equal to 0, it's invertible, right? And if it is equal to 0, not invertible. Yes, so what we're going to do is we're going to restrict it. So there's a notation in your book. Your book uses GL2R. It's called the general linear group. These are, before I define it as a group, GL2R, it's the set of 2 by 2 invertible matrices. Okay, now you should be careful, right? Oh, sorry. Let me just say one more thing. Also, it's closed under. Let me just write something. Where is it? I mean, and it's pretty clear that we need it to be closed under, you know. Yeah, I mean, it's sort of assumed, but like, it's closed under the operation, right? So, because if you leave G, it doesn't really make sense. I guess that's sort of implied from associativity, but so from here, what do you get? So why is this closed, right? So if I multiply, if I consider GL2R under multiplication now, the third property holds now, right? Everything has an inverse because everything's invertible. So really, you should check that, is it true that, I guess, is it true A times B is equal to, is in GL2R, given A is in GL2R and B is in GL2R. Yeah, I mean, all the other ones were, because, I mean, if you add 2 integers, they're still an integer. I guess we didn't really need to check that. But in this case, maybe we do need to check it. So if I multiply 2 invertible matrices, do I get an invertible matrix? Is the question. So if I what is the relation of this, right? Hopefully you all remember this is true. Yeah. So if these 2 were non-zero, this has to be non-zero because it's equal to the product, multiply, the product of 2 non-zero things, right? So you see, if A and B are invertible, A times B is invertible, right? So you see that it's actually close. So and then similarly, if it's multiplication, this is your identity, right? I mean, hopefully you all know the identity matrix because A, B, C, D times 1, 0, 0, 1 is A, B, C, D. Yeah. So you can see that you could do, I mean, you could write it out more explicitly, but this forms a group. Yeah. Now, the nice thing about this is, let me just say, this is our first example where it's not abelian, right? So recall right here, right? We don't have the requirement that A times B is B times A, right? So in this case, as you know from Math 3A, if you multiply two matrices, they might not be equal, right? I mean, I don't want to not equal. How do I write this? Might not be. Might not be equal to B times A, right? Most of the time. In fact, most of the time it's not, right? If you multiply two matrices, it doesn't really commute, right? So this is an example of a non-abelian group, right? It's a group, but it doesn't satisfy the property that like A times B is B times A for all AB in our group. Okay, everyone good so far? Okay, hopefully that's enough examples so I can move on. So let me just say these are results. I mean, they're propositions / theorem from book. The first thing is the identity is unique. And this is proved just from the group axioms. Yeah, you're not using anything else. So the inverse is unique. So basically it's saying you cannot have two identity elements. You cannot have two inverses. And it's clear that if you do the inverse of the inverse, it's A. Yeah. And next, groups have cancellation property. So it's what you like. So if BA is CA, then B equals C. So basically, can cancel the A. That's why it's called cancellation property. And next, if AB is AC, then I don't know why I put the input comma. So this looks redundant, right? But again, A times B might not be B times A. So we actually need both left and right cancellation properties. If your group is abelian, you don't need the second part, right? Because A times B is B times A, and C times A is A times C. Okay. So in your book, it says law of exponents. So be careful here, yeah? So hold. So this is why you should be careful when you read the book. So g to the m times g to the n is g to the m plus n. So do not think of this as as multiply. Yeah. So when the book writes g to the m, they mean this, right? M times, where circle is your operation, right? So if the group operation was multiply, let me just write if circle was multiply, then it is what you think, right? It's like g squared is g times g was multiply, then it is what you think, right? But for example, when someone writes integers under addition, right? If I write 1 to the 5th, this is one circle, one circle, one circle, one circle, one. but my operation is plus, right? So this is 1 plus 1 plus 1 plus 1 plus 1, which is 5, right? So that's why I'm saying don't think of it as like 1 to the 5th power, right? It's like it's to the 5th power, but like under your operation. So is everyone clear on this? Hopefully I'm not confusing any of you. It's very weird notation, but yes. So again, if you're given a group, you can only, do stuff that's under its operation. Yeah? A group comes with an operation, and elements interact through that operation. You can't just change it midway. So, okay, and similarly, 2g to the mn is gmn. I mean, it's everything you think. So gh to the n is g to the n, h to the n, if g is abelian. So why is this true? So let me just convince you. Gh squared is gh circle gh, right? So let me just, by gh, again, let me make a note here. This thing, it does not mean multiply, it means this, right? So if in integers, this would mean g plus h, right? But people, if the operation is understood, we just write gh. So what does this mean? This is g circle g circle h, right? So, but that's what it means to be, sorry, yeah. So now if we are abelian, we can swap this, right? Because h circle g is g circle h, if g is abelian, right? So this is g circle circle h, which is g squared h squared. So you could see, that for, I mean, I did it for, in the case n is 2, right? You use induction to prove it for all naturals, right? So moving on, what is the inverse of g circle h? Or book writes gh for short. Yeah, but yeah, so what's the inverse of gh? Anyone? It's a bit tricky. It's like it's actually like, is h inverse compose g inverse? It makes sense, right? Because if I multiply h inverse g compose g inverse, these two become identity, right? So this is g compose e compose g inverse. Now using the identity property, g compose e is g, and then this is e. Yeah. The book writes it like this. So for short, this is for short. Yeah. So again, do not think of this as like multiply. It's under your group operation. Okay, is everyone clear so far?
Can we exchange the order of H inverse and G inverse there?
No, you can't, because you want to say this, right? So you want to say, is this what you're asking?
Oh, yeah.
Okay, well, let's check it, right? So if I compose, if this is actually the inverse, when I compose, I mean, not compose, when I do the operation, I should get E, right? That's what it means to be the inverse, right? Like G compose H compose, right? I mean, if you think of G compose H as A, I'm just saying this, right? So this should be true, but you don't know if this is true, right? Like how are you gonna get E from like the left-hand side? You can't, right?
I
If
mean,
G,
based on the third property, like that the inverse elements in G, like A times A circle A inverse is equals to A inverse circle A is equals to G. So I
Yeah,
don't know.
I agree that G composed G inverse is G inverse composed G, but you don't have that right now, right? You have G composed H composed this, right?
Oh, I see. Yeah, okay. So it has to be a group first to have this property.
Huh? No, I'm saying I'm saying G inverse composed H inverse may not be the inverse. Be inverse of G composed H. I mean, given group G. So if G is abelian, then it is, right? Because what I can do is, since it's abelian, I could swap these two, right? So this becomes G composed G inverse, composed H inverse. And then this is E, and this is E, so it's E, yeah? But the problem is in general, you cannot swap, right? You can only swap if G is abelian, right? What I mean is, if I go back again, I put it in blue, right? Yeah, right here. It's not true that A compose A circle B is B circle A, right? So you don't have that, sadly. So is everyone clear so far? It's very, yeah, it could get a bit pedantic. So everyone good? So you see here the H inverse G inverse. I did not switch, right? I just use, this is by the third property of a group. When you do the inverse, you get E, right? And then from here, I'm using the second property of a group, that G composed E is G. And then here I'm using the third property of a group, right? When you compose with the inverse, you get identity. But you see for here, you need this extra assumption to like swap your terms. And that's not part of a group, right? That's only if the group is abelian. Okay. Everyone good. Okay, so given a group G, so we could think of subgroups now. A subset H. Oh, sorry. A subgroup H. We all know what a subset is. H is a subset of G that is itself a group under the operation of G. Yeah, so an example would be, they call it, the book denotes it SL2R inside GL2R. Let me just write, the book doesn't write this, but it's under multiply, right? So remember these were invertible 2x2 matrices. And then this thing is invertible 2x2 matrices of determinant 1, right? So remember, to be invertible, you just need determinant is non-zero, right? So here, determinant can be like 5,000, right? But here, these are all matrices of determinant 1. Now, why is this in itself a group? I think that the hardest thing to check is, whether it even, if you multiply two things, is it still determinant 1? And it's by this property, right? The thing that saves it is this, right? You see that if it was if instead of 1 it was 2, it would not be a group, right? Because the product of the two would have determinant 2 times 2, which is 4. So you don't remain in your group. So you see determinant 1 is important because 1 times 1 is 1. So yeah, that's an important part. So note under operation of G is important, right? So for example, I can have two groups that are subset or like as a set is a subset of the other, right? So an example would be GL2R. This is a subset of all 2x2 matrices, right? And this by itself under multiply is a group. We went over this, right? And this under addition is a group, right? These are both groups. And as sets, this thing is a subset of that, right? But this is not a subgroup of, not subgroup. I need to check what they use for notation of subgroup. Some books use this, which like less than or equal to sign, but okay. Let me just, not subgroup of mat to R under plus. So note that they both are groups, right? So everything here, a subgroup H, so that it is a group, it is a subset, but it's not under the operation, right? Because here you're not taking the same operation. You're switching operations. You're going from plus to multiply. Here it is. Sorry. Yeah, I'm gonna use less than or equal to. So here it is, right? Because I'm inheriting it from my bigger set. Here is multiply. Here is multiply. But here I'm going from plus to multiply. So these two are groups, but one is not a subgroup of the other. Everyone clear? Okay. So so now how do you check something as a subgroup? So subgroup check. This is a proposition in book. I mean, surely you need to check one identity E is in G. 2, if H1, H2 is in H, it's H1, H2 is in H, so it's closed, right? As you can see from above, I told you if it was determinant 2, it would not be closed. And 3, if H is in H, H inverse is in H. So why is this important? Why do we need to check this? So let's think it through. If I have a subset, right? The inverse certainly exists, right? Because if G is a group and H is a subset of G, then certainly if H is in H, H inverse is in G, right? Because I mean, if H is in H and H is subgroup, H is in G, right? And since H, let me just write that like this. If H is in G as G is a group, H inverse is in G. The problem is H inverse might not be in H, right? That's the issue. That's why you need to check this, right? So certainly H inverse exists, right? So no doubt about that. But the problem is it might not exist in your smaller set, right? It certainly exists in your bigger set because we assume it's a group. So everyone clear so far? Okay, so really quick, so you could check these 3 properties, and then the book says, or you can check H is not the empty set, and for all G, this is the faster way. Honestly, it's about the same. It's about the same time to write. So you check GH inverse is in H. Either way, yeah. I mean, that's how you check something is a subgroup, given a group. Yeah, so given a group, that's how and I give you a subset, this is how you check that subset is actually a subgroup. So again, this is under your operation, right? This means G circle H inverse. Everyone clear? Hopefully that, makes groups more clear to everyone. I hope. Again, reminder, your quiz is due like tomorrow night, I think. It's like 3 questions. It should take you like 5 minutes maximum. If you know your stuff. Okay. But you do have 25 minutes, so. Okay, I'm gonna stop recording.